One of the objectives of calculating conditional probabilities is to determine whether two events are related. Specifically, we want to know whether they are independent, and by that I mean the probability that one event is not affected by the occurrence of the other event. So, in mathematical formulas, we say two events are independent if the conditional probability is equal to the marginal probability. So, this first one here, probability of A given B is equal to probability of A. What that means is that that condition of B occurring or not has no effect on the probability. Likewise, if I say the probability of B given A is equal to the probability of B, then in this case, the probability that A occurs, whether or not A occurs, has no effect on the probability of B occurring. If there is a relationship, that is, if these are not equalities, then these events are called dependent. So recall, earlier in a previous video, we found the probability that a randomly chosen person buying Elmo, given that they've seen the ad, was 40%. Well, just in general, those who saw it bought Elmo was 30%. That is, having seen the ad made the probability go up. So in fact, we can conclude that seeing the ad is effective in increasing sales, and would say that the probability of buying a talking Elmo depends on whether the customer saw an ad. For another example, consider this following table of soft drink preferences. So on the one hand, we're looking at people who are under 20 versus over 20. On the other hand, we're dealing with Sierra Mist or Sprite. So what we want to know is there a drink preference based on age? Well, let's first look at the probability that someone chooses Sierra Mist given that they're under 20. So in this case, we're looking at these 500 people who are under 20. Out of these, 310 would prefer Sierra Mist. So the probability is 310 out of 500, or 62%. Out of those who are over 20, we're going to look at this 500 here, so same number, but different 500. Out of this row, 310 would prefer Sierra Mist, so the probability is actually the exact same, 310 out of 500, or 62%. Overall, if I just pick a random person, regardless of age, and figure out their preference, well, 1,000 total, 620 preferred Sierra Mist, 620 out of 1,000 is 62%. Notice in this case, whether they're under 20, over 20, if we just took the entire group, the probability is 62%. So in this case, drink preference and age are independent of each other. And that is, the probability of drink preference does not change with the age group. Those are under 20 and over 20, same probability. What if I want to look at drink preference and gender? So if I go about the same way, let's start off Sierra Mist, given that we're looking at males. Well, there are 550 males overall in the study. 400 of them chose Sierra Mist, so 400 out of 550 is about 73%. On the other hand, if I'm looking at the females, there are 450 females overall. Only 220 of them prefer Sierra Mist. 220 out of 450 is about 49%, considerably less than the males. Overall, the probability of choosing Sierra Mist, as we found before, 620 out of 1,000, or 62%. So in this case, these are not independent. Whether or not a randomly chosen person prefers Sierra Mist, that probability depends on whether they're male or female. So the probability of drink preference depends on the gender of the participant. One last note, independence is a very strong assumption, so we need to be careful and verify it is true before we assume it holds for two events. So what is the problem of assuming independence? Well, in general, joint probabilities are often difficult to find, so assuming independence can be very helpful because, as it turns out when it comes to probability of independent events, You just multiply the probabilities together. If they're non-independent, then it gets to be a lot more complicated. But as my next example shows, bad things can happen when you blindly assume independence.